Calorimetry is a technique that we use in the lab in order to determine how much heat is either produced or absorbed by a reaction, or by burning something, or how hot something may be. We typically tend to transfer heat, especially of things that are solid, to something that's more measurable, like a liquid water is most commonly used. So to know how all of our foundation of this calorimetry works, it's a simple equation, and that is that the heat of the system is the inverse of what goes to its surroundings. So if you've got something hot, it's going to transfer that to its surroundings. And so it loses the same amount of heat that the surroundings will gain. And vice versa. If something's really cold, then it's going to take energy from its surroundings. And so it's a negative relationship from one to the next. Another way to see this equation is simply with delta E, because delta E, change in energy, is often used synonymously with Q. So just so you know that. So remember that there's a law of conservation of energy. And that law states that energy cannot be created or destroyed. It's only transferred from one object to the next. So we use a lot of this calorimetry. Basically, this is the device where you have some type of reaction chamber, and then outside that reaction chamber, usually you have some liquid, very commonly water, and you've got a thermometer set up. Now y'all know I can't draw, and I'm sorry, but that's the case. So you've got a temperature probe. You can tell how much heat is transferred to that water because you're monitoring the temperature. You do have to sit there for a minute or two and say, okay, is that really the highest it's going to go? And sit there and doubt yourself a few times, but that's okay. That's exactly what calorimetry is. So exothermic reactions, what we talked about last time, will show a rise in temperature because they're releasing energy. And endothermic reactions will show a decrease in temperature. In other words, the temperature will go down. So most commonly we give examples that require exothermic reactions, but that does not mean that endothermic reactions don't happen. They absolutely do. Okay, so we often use what's known as coffee cup calorimetry to see how much heat is going on and what's transferring, but it's not hugely accurate, and it's actually using kind of what you know as a coffee cup, like a styrofoam cup, one inside the other. But to use this for calorimetry, we need to rearrange some of the specific heat equations that we talked about last time. So there was two of them that we talked about last time. We talked about specific heat, which is right here, and we talked about general heat. So either of those can be used. All you have to do is just solve for Q. And honestly, these are used more often. This form of the equation is used more often. And we're going to use this a lot today. So you're going to see me substitute the right side of these equations in for Q because it's just easier to do it that way. Do realize that there's a difference between little c and big C, but how we can tell a difference as far as moving forward in these problems is that little c will have a gram because of that mass function that's there, and big C does not. But both of them will give you energy or heat in the end, okay? So let's try some examples with this calorimetry bit. So let's say that we have a 200-gram piece of steel, and you're adding that to a 500 milliliters of water. That water's initially at 22.5 degrees. After the steel's in the water, the temperature of the water goes to 47.3 degrees. Now you assume that that means that the steel and the water are the same temperature at that point. And what that's saying is that they reach what we call equilibrium, where both of those are kind of equal. They're not giving or sharing energy in any capacity to the other one. So the question is, what was the original temperature of the steel? And it gives you some constants. We know that steel has this constant. Well, that is the heat capacity because we've got grams here. And then water has this heat capacity. Okay, so we've got some information here. It may seem like you don't even know where to start. That is okay. I do want to point out the fact that we've got Kelvin over here, we've got Celsius over here. Remember, those are synonymous in this case, so it doesn't really matter. We can switch that to either Kelvin or Celsius without a problem. So here's where we begin. We said that Q of the surroundings is equal to the Q of the system is equal to the negative Q of the surroundings. Well, in this case, steel is what is the system, and the water is the surroundings. So now what we can do is we can say all of this is that heat capacity equation. And all of this is also the heat capacity equation. It's just that over here we have steel, over here we have water. That makes it a lot easier when we actually have a formula to follow, right? Another thing that these types of problems often don't say, but they assume that you know, is that we're going to assume the density of water is 1 gram per milliliter. So if you're given a certain number of milliliters of water, you can go ahead and convert that to grams as long as you're not given a different density for whatever solution you have there. One other thing to remember is that when we're talking about change in temperature, it's the final temperature minus the initial temperature. So when we put this in, sometimes we actually have to put in the T final minus T initial. But the final temperature for both of these should be the same thing because they have equilibrated, which is 47.3 degrees. So now we just basically plug numbers in and find our solution. So we've got that steel has this heat capacity, there's 200 grams, and our final temperature is given right there. Then we know that this is what we have for water. Now, that means that the initial temperature of steel, if you go through and complete this, is actually 514 degrees Celsius. That's quite hot. So yeah, pretty cool, huh? That's really all you do. Make sure that your math is correct, your algebra is correct when you solve this. Make sure that you can do this calculation in your calculator and you come up with the same value there. I hope that I'm right. Okay, leave me a comment if I do mess anything up there. Another type of problem that you might see is that you actually combine two things together. Most often this is things like sodium hydroxide and HCl. Those of you who are with me may see that in lab soon. So the question here is how much energy is released when you have magnesium and it's added to enough HCl to make 100 milliliters of solution. The solution goes from 25.6 degrees Celsius to 32.8 degrees Celsius. And it gives you a solution density, it gives you the CS of the solution, in other words, the heat capacity, the specific heat capacity. And then we know that this is the equation. Now, in this case, we don't need to know how much that is because we're only being asked for how much energy is released. Okay? We do need to know how many grams of solution we have. So we can convert that really easily with the density. So 100 milliliters should be 100 grams, which it is in this case. So we're going to take our equation. The Q technically of reaction is equal to mass times heat capacity times change in temperature. So we just plug in some numbers. Oh, I forgot to put in the change in temperature here. And that is 7.2. So that's sort of what we should have there. Again, Celsius and Kelvin in this case can cancel out. You could call that Kelvin instead of Celsius. That's totally fine. So you should get around 3,000 joules. Second time I calculated that, I got 3,012. But it doesn't matter because when proper sig figs, it should be just two significant figures. Now, why is this negative? Well, truth be known, we should have had a negative here because we are releasing energy into the environment, right? Into the surroundings. So that's what that negative means. These types of equations, sometimes you have to process thought at the end and go, is that negative, is that positive? And you'll see that a little bit more when we talk about delta H in the next video. Let's try one other type of problem, and that is within bomb calorimetry. So in bomb calorimetry, you literally take a sample and combust it. You burn it into ash inside a chamber with excess O2 gas. So you've got plenty of O2 around. It just kind of goes, it kind of does what it says it does. And water is going to surround the chamber. So you measure the change in temperature in the surrounding water, and we can tell how much energy was actually coming from that sample. So here's our equation. We could say that Q of the of whatever heat you have is from the calorimeter and the change in temperature. But we also have to keep in mind that there's water there. So we have to add the heat from the calorimeter and the heat from the water together to get the Q of the reaction. So here's what I mean as an example. We have 2 grams of wood and it's combusted in a bomb calorimeter with a heat capacity that's given here as 790 joules over degrees Celsius. There's 815 milliliters of water inside the calorimeter, and we know what the temperature change was. So how much heat was produced? Well, the Q of reaction here is going to be the negative value of what's happening in the water. And we can assume that that's 1 gram per milliliter, like I said before. And the heat that is within the bomb calorimeter. Now, this was given to us in a form of big C. Notice over here, we don't have any mass in our units. That's fine. We don't need to worry about that. That's actually easier because we don't have to put in something else in our calculations. But we do have to assume that the heat change that took place in the water was the same as what happened in the calorimeter. So that means that the Q of the reaction is going to be equal to the Q of the water, which is mass of water times C of water times change in temperature, plus the Q of the bomb calorimeter, which is the C of the calorimeter times the change in temperature. So the change in temperature is the same in both cases. Let me move this up just a little bit here. And we just plug and chug at this point. So we've got 815, we've got our C of water, change in temperature. We've got our C of the big C of the calorimeter and the change in temperature. And we just find what that Q of reaction is. You do have to watch your sig figs because these numbers can get very large, and realize that this is still a negative value because that's what's being released and causing the temperature increase in both the water and in the calorimeter. Okay, I went over that pretty fast. You should probably go back and watch these and try these on your own. Good luck. Thank you very much.